This is the second video on theory of estimation. Efficiency of an estimator is computed like this. If T1 is the minimum variance unbiased estimator and T2 is any other unbiased estimator of theta, then the efficiency of T2 can be calculated as variance of T1 by variance of T2. So variance of T1 will be the least because it is the variance of minimum variance unbiased estimator. So a least number is divided by a number which is greater to it. So always this E efficiency will be less than or equal to 1. Similarly, if T1 is an efficient estimator of theta and T2 is any other consistent estimator of theta, an estimator is called efficient estimator if it has the least variance among the consistent estimators. Okay, so here efficiency is calculated as variance of T1 by variance of T2. Here again efficiency is always less than or equal to 1. And the correlation coefficient between an efficient estimator and any other consistent estimator is square root of E. The Kramer-Rao inequality, it gives a lower bound for the variance of an unbiased estimator. If T is an unbiased estimator of gamma theta, then variance of T is greater than or equal to gamma dash theta the whole square divided by expectation of dou log L by dou theta the whole square. If the variance of any particular estimator is equal to this lower bound, then that estimator will be called the minimum variance bound estimator, right? See, an estimator whose variance is equal to this bound. This is the lower bound for the variance of an unbiased estimator. Variance of an unbiased estimator will be greater than or equal to this number. But if the variance is exactly equal to this number, that estimator will be the minimum variance bound estimator. So, how to search for a minimum variance bound estimator? This is the shortcut, right? You compute dou log L by dou theta, and if you are able to express it in the form A of theta into T minus gamma theta, you can say that T is a minimum variance bound estimator for gamma theta. Okay, these are the points to remember. And Kramer-Rao inequality gives the lower bound for the variance of an unbiased estimator. If the variance of an estimator is equal to Kramer-Rao lower bound, the estimator is called minimum variance bound estimator. And this is the necessary and sufficient condition for an estimator to be the minimum variance bound estimator, right? A statistic T is sufficient to estimate theta. This is Neyman's factorization theorem. If T contains all information about theta, you cannot just divide this function into a function of T and function of theta. If that is the case, you can say T is a sufficient statistic for theta. Then what is the purpose of Blackwell theorem? Any function of a sufficient statistic is an unbiased estimator to its expected value. So this Blackwellization, this process, any function of sufficient statistic will be an unbiased estimator to its expected value. This is actually the theme of Blackwellization. You try to find MVUE through sufficient statistic. That is the idea. And the maximum likelihood estimator, it maximizes the likelihood function. The likelihood function is the probability that x1 takes the value x1, x2 takes the value x2, etc. xn takes the value xn. And the function which the value of theta which maximizes this L is called maximum likelihood estimator. And these are the some of the points you should remember. For maximum likelihood estimator of lambda of Poisson distribution, it is x bar. Maximum likelihood estimator of mu in the case of normal distribution is x bar. If mu is known, the maximum likelihood estimator of sigma square is summation x minus mu the whole square by n. If mu is unknown, the MLE of sigma square is summation xi minus x bar the whole square divided by n. In the case of Bernoulli distribution, MLE of P is summation x by n. If x follows binomial distribution, MLE of P is x by n. And if this is the form of exponential distribution, MLE is just x bar. If this is the form of the exponential function, MLE of theta is 1 by x bar. Right? These are some, it will be fine if you remember these points. And the properties, MLE is a function of sufficient statistic, always true. MLE may or may not be unbiased. For example, you know S square is a biased estimator of sigma square. But this S square is a MLE of sigma square. So this S square may, based on this point you can say MLE may not be an unbiased estimator of its parameter. MLE has invariance property, that is if T is MLE of theta, then xi of T will be the MLE of xi of theta, right? Only consistent estimator and a maximum likelihood estimators have invariance property. MLE is efficient and MLE is consistent, right? These are some of the points which you should remember. Let us now go to the questions, right? If T1 is the minimum variance unbiased estimator of theta and T2 is any other estimator of theta, what is the correlation between T1 and T2? The correlation between T1 and T2 is square root of E. Okay, square root of the efficiency E. If T is a consistent estimator of theta, then the consistent estimator of theta into 1 minus theta. See, if T is a consistent estimator of theta, any function of T will be the consistent estimator of the function of theta. Okay, so theta minus theta into 1 minus theta is equal to theta minus theta square. Then the consistent estimator will be T minus T square, or it is T into 1 minus T. You check whether any of these forms are available in your options. T minus T square is there, so you can say this is the right alternative, right? Now, which of the following is true about consistent estimator? Expectation of T tends to theta and variance of T tends to infinity. No. Expectation of T should go to theta and variance of T goes to 0 as n tends to infinity. This is the right answer. Let us also check the other alternatives. Expectation of T tends to 0. No. Expectation of T tends to theta and variance of T tends to theta. No, that is not right. So expectation of T should go to theta and variance of T should go to 0 when as n tends to infinity, because consistency is an asymptotic property. Kramer-Rao inequality gives the lower bound for the variance of an unbiased estimator, the lower bound for the expectation of an unbiased estimator, the lower bound for the variance of a consistent estimator, the lower bound for the variance of an efficient estimator. It gives the lower bound for the variance of an unbiased estimator. Okay. If the variance of an unbiased estimator is equal to Kramer-Rao lower bound, the estimator is called minimum variance unbiased? No. Minimum variance bound estimator? Yes. Okay. If the variance of an unbiased estimator is equal to the Kramer-Rao lower bound, then the estimator is called minimum variance bound estimator. Which of the following is Kramer-Rao inequality? This is the correct option. Variance of T greater than or equal to gamma dash theta. No. Gamma dash theta the whole square divided by option D is correct. Expectation of dou log L by dou theta the whole square. Is now the next problem. The necessary and sufficient condition for an estimator T to be a minimum variance bound estimator is no gamma dash theta. This is not the right option. This is also not correct. The option A is correct. Dou log L by dou theta is equal to A of theta into T minus gamma theta is correct. Okay. Next. Which of the following is true according to Blackwell Theorem? Any function of unbiased estimator is a consistent estimator to its expected value. No. Any function of sufficient statistic is an unbiased estimator to its expected value. Any function of sufficient statistic is a consistent estimator. No. The option B is correct. Okay. Fine. If T is the MLE of theta, what is the MLE of theta square? T square, because MLE has invariance property. Bias of an estimator is always negative. You cannot say always positive. No. Always 0. Definitely no. It can be positive or negative, and an estimator can be negatively biased or positively biased. The theorem which enables us to obtain MVUE through sufficient statistic is Bogner's theorem, Pearson's theorem, Rao-Cramer inequality, Rao-Blackwell theorem. Efficiency of an estimator is always less than or equal to 1. Okay, by Neyman's factorization theorem, T is a sufficient statistic if this one or this one. The first option says that T contains all information about theta, due to which I am not able to separate this function into a function of T and function of theta. So this is the correct option. 21, option A is correct. Which of the following is false? MLE has invariance property, it is true. Consistent estimators have invariance property, it is true. Efficient estimators has invariance property, it is false. MLE may or may not be unbiased estimator, it is true. So the correct option is C. Which of the following is false? MLE is always unbiased. No, may or may not be unbiased. MLEs are efficient is true, consistent is true, invariance property is true. So this is false. Which of the following is the likelihood function of binomial distribution? See, in binomial distribution, the likelihood function and probability function are the same. Okay. This is the probability function and the same is the likelihood function, because you obtain binomial distribution as the convolution of Bernoulli variates. So you should not find likelihood function as product of f of x1 into f of x2. That should not be done. Actually, for binomial distribution, the likelihood function and the probability function are the same, right?